Hello, everyone. Thank you for joining us for today's presentation. This is the seventh of 8 presentations between AMCA and Odell Associates. And I am putting the presentation on screen for you all. Hopefully you can see it in presentation mode. Pat, can you confirm for me?
Yes.
Perfect. My name is Lisa Cherney. As you all who have attended previously know, I am the Education Manager for AMCA International. A couple of housekeeping notes for you all. We do have the audience muted for the program. And if you have any questions that you think of during the presentation, please feel free to submit them via the Q&A panel on the right-hand side of your screen. We are recording today's session, and that recording, along with the PDF version of the presentation, will be posted on the Odell website within about 48 hours. If you want to earn PDH credit for today, please remember that you do need to stay online for the entire hour and then complete the survey, which will be emailed to everyone after today's program. And even if you do not want PDH credit, we would love to get your feedback on that survey. Again, to submit a question, you go to your interactive panel, select the Q&A option, type your question in the box and click send. I do remind everyone that all chat messages and all Q&A questions can be seen by everybody in the audience. And if you have a question that's a bit too involved to type out, please go ahead at the end of today's program during Q&A, use the raise hand feature at the bottom of your screen, and we can unmute you. For PDH credit, AMCA International has met the standards and requirements of RCEP. Credit earned for today's program will be reported to the RCEP website, and you will receive an email from them that summarizes credit earned and allows a link to a printable certificate. We have a quick disclaimer that the information today is provided as an educational service only, and it is not intended to serve as professional engineering and/or manufacturing advice. The views expressed today by our presenter are of his alone and do not necessarily represent the views of AMCA. In making the activity available, we are not endorsing, sponsoring, or recommending any particular company, product, or application. And under no circumstances, including negligence, shall AMCA be liable for any damages arising out of a party's reliance upon or use of the content contained in today's program. The program is copyrighted by AMCA International, and I would like to introduce to you our presenter for today. Mr. Pat Brooks is a senior project manager at SMACNA. He has over 35 years of experience in HVAC ductwork design and manufacturing. Pat earned his bachelor's and master's degrees in mechanical engineering and also holds another master's in business. He is a member of ASHRAE and SPIDA technical committees on duct design, and he was recently named ASHRAE Distinguished Lecturer. And before we get to today's objectives and the rest of the presentation, I will stop sharing my screen because we have a poll question for the audience. So you should see that on your screen. And the question is, do you use the ASHRAE duct fitting database? And if you all would go ahead and vote on that, either let us know, yes, you do, no, you don't, or I'm sorry, I'm not aware of what that is. We will give you a few seconds to do that. And then we will show the results on screen. So we'll give it a couple more seconds here for anyone who is just joining or just voting. So I'm going to close the poll here. and we will show the results on stage. So hopefully everybody can see those responses. Just over 27% say yes, they do use the database. About 9% say no, I do not use it. And a little bit more than 63.5% say I'm not really aware of it. So with that, I'm going to hide the poll and now turn the presentation over to Pat. And Pat, you can go ahead and share your screen and carry on.
Are you seeing my screen?
We are, and now we just need presentation mode. Perfect. And Pat, just if you want to hide that little banner at the bottom. Perfect.
All right. Well, good morning, everybody. Hope you're all doing well and hopefully COVID-free. Not that it affects anything since the seminar is remote. But the first slide is the purpose and learning objectives. And the purpose of this presentation is to teach the fundamentals of supply duct design and pressure losses. So we're not going to go into great detail, but at the end of the presentation, you should be able to describe friction and dynamic losses as well as fitting selections, identify the various duct shapes, and you're probably already aware of at least two of them, calculate the initial size, and then we'll kind of explain the system layout, use of loss coefficients and friction calculations, and talk a little bit about equal friction versus static regain and what is total pressure design. So we're going to really start out with the fundamentals. First, a lot of this information is in this ASHRAE Duct Systems Design Guide. It's recently published. Herman Beals was the main author. Unfortunately, Herman passed away a couple of years ago, but it's quite comprehensive on duct systems. It's supply, exhaust, and also teaches acoustics. All right, so we want a high performance air system. So what are the goals to get there? Well, we need to design energy efficient HVAC systems that deliver the proper amount of air. We want to design balance systems that minimize fan energy use and minimize first cost. And we want to minimize the maintenance costs. We also want to keep noise levels within the required NCRC levels. That's another seminar on that, so we'll talk about it a little bit, but not in great detail. And we want to provide a comprehensive design to the owner per the owner's project requirements. So we want the customer to be happy. Very fundamental is cross-sectional areas. Round duct is pi d squared over 4. Rectangular is WH. You're probably pretty familiar with those. And then the common one that has become more common is flat oval. And that area is equal, as shown there. It's a pi a squared over 4 plus a times a minus a, where the a's are little or large according to the figure. Now what this is you've got two half circles on either side. Put those together, that's the pi a squared over 4. And then you have this box in the middle, which is the flat span times the height. And the flat span is the big A minus the little a. Staying with basic equations, the velocity is equal to the flow rate divided by the area, or the area is equal to the flow rate divided by the velocity, or the flow rate is equal to the velocity times the area. I didn't write that last one down, but you can see how those are derived. So a quick example, and these examples are in English and SI units. I'm not going to talk too much about the SI units, but they're there. So the question is, if the volume flow rate in a 22-inch duct is 5,000 CFM, what's the average velocity of air in the duct? So D equals 22. We're going to convert that to feet. So we get the area in feet, and that's equal to pi times 1.83 divided by 4. And the 1.83 is squared. That gives an area of 2.64. So we take the flow rate, 5,000, divide by the velocity, and we get, divide by the area, and we get the velocity of 1,894 feet per minute. So pretty straightforward. Most of you are going to know that. Example 2, if the design volume is 13,000 CFM and the velocity is 4,000 feet per minute, what's the H dimension of a rectangular duct if the W dimension is 14? Well, the area is equal to Q over V, so that's 13,000 divided by 4,000 is 3.25 square feet. We're going to multiply that times 144 to get it in inches squared, so 468 inches squared. And then we solve for the H in the equation AD equals WH, so H equals AD over W, and that's 468 over 14, or 33.4 inches. Some more basic equations, a conservation of mass. This assumes air is not compressible. But the volume flow rate before flow divergence is equal to the sum of the flows after divergence, or QC is equal to QB plus QS. Now, still some basic equations, but some important ones. The total pressure is defined by P sub T. It's equal to the static plus a velocity pressure at any point in a duct system. So you can see if you put a pedostatic tube in the air, what's impinging on the front is the total pressure. What's around the sides is the static pressure. And the difference between the two, as shown by the manometer, is the velocity pressure. So total pressure represents the total energy of the air flowing in a duct system. And we like to use total pressure as much as we can in the analysis. Energy cannot be created or increased except by adding work or heat, typically at the fan. Energy, and thus total pressure, must always decrease once the air leaves the fan. Total pressure losses represent the irreversible conversion of static and kinetic energy to internal energy in the form of heat. The losses typically are classified as friction or dynamic. We'll talk more about those. Now, static pressure is a measure of the static energy of air flowing. Air which fills a balloon is a good example of static pressure. It's equally exerted in all directions. And a bit of trivia, if you want to know, the static pressure at sea level is 14.696 psi. 1 psi is about 27.7 inches of water, and that means 1 atmosphere is about 407 inches of water. Now, it's important to understand static pressure will decrease when there's an increase of velocity pressure. So some of that static's being converted to velocity. Now, static pressure can increase if there is a decrease in velocity pressure, as some of that velocity pressure is converted to static. The velocity pressure is always a positive number in the direction of flow. It's a vector quantity. It will increase if that cross-sectional area decreases, and it will decrease if the cross-sectional area increases. When velocity pressures increase, static pressure must decrease. But when velocity pressure decreases, there can be a gain in static pressure, commonly called static regain. But if the losses are too great, you may not get that regain. The velocity pressure has a couple of equations. The main one is the PV equals rho times the quantity V over 1097 squared. So the PV is in inches of water, velocity is in feet per minute, and rho is the density. And there's an equation for the SI as well. For standard conditions, rho is 0.075 or 1.204 kilograms per meter. And when you do that, this top equation becomes V over 4005 squared. You want to write that down. Okay, let's talk about changes in pressure. I'm going from one point in a duct system to a second point. So there's a little triangle there in front of P. That's the Greek letter delta. And as far as this goes, that means change. So the change in total pressure has to equal to the change in static pressure plus the change in velocity pressure. That's derived from the Bernoulli equation. And typically we ignore elevation. It doesn't have much of an effect. But if we look at this equation, we have basically the static pressure plus velocity pressure at point 1 is equal to the static pressure plus velocity pressure at point 2 plus the losses. So that's how that delta PT is equal to delta PS plus delta PV. Now let's look at a typical design leg. We'll talk about what that is later. But the pressure drop is a gradient along the duct system. So we start out at 0 out here outside, and it starts to accelerate, and we start to lose total pressure, and it always has to decrease until it gets to the fan. Then it will increase, and then it will decrease again. So this top line is the total pressure, and note it's not 0 at the exit, not 0 till a little bit away from the exit. We'll talk about what that means. Static pressure, however, can decrease or it can increase when you have a decrease in velocity pressure. So here's where the velocity pressure decreases on that fitting, that transition. The static pressure is actually increasing. And again, at the fan, it increases and then it decreases again. And depending on what the velocity is doing, increase or decrease. And then you get to the outlet and you see it at the outlet, the static pressure is 0, but the total pressure isn't 0 until you come out a little bit further. And that difference is the velocity pressure. So you still have some total pressure as your exits in terms of velocity pressure. And the difference in these two graphs at any point in time is the velocity. So you can see it at this level, then it increases because the duct decreases. And you go through the system like that, where the duct increase, the velocity when the duct increases, the velocity pressure decreases. Okay, so what causes these losses? Friction losses, which are caused by molecules interacting with each other, air molecules interacting with each other in the duct wall, and dynamic losses, which are mostly associated with fittings, where you might have a change in size or flow rate or construction. Excuse me for just a second. Now, the Darcy-Weisbach equation was developed to account for the losses. The left-hand side of the equation is the Darcy, and that's the friction loss. And the right-hand side is the fittings, identified by a loss coefficient times the velocity pressure. Now, these coefficients, what we're going to use is the ASHRAE duct fitting database, and it can be used actually to determine the friction loss and fitting losses and coefficients. It includes over 200 types of fittings. Now, in that equation, that prior equation, one of the factors is the friction factor. So we have to determine that. And we can use the Colebrook equation. And the Colebrook equation, I'm not going to read it out, but you can see that it's a function of the square root of f on both sides. And so it's impossible to solve that mathematically. So you have to solve it iteratively. And you do that by you plug in an f and you see if you get the same result on both sides. And eventually, doing that iteratively, you can determine the friction loss. But note, it's also a function of that, what looks like a scribbled E. That's the Greek letter epsilon, and that is the roughness of the material. And DH is the hydraulic diameter, and then RE is the reference. There's a Reynolds number. Now, the roughness are determined experimentally, and you can see in this chart, I'll blow it up a little bit, and it gives you the duct material type and the absolute roughness in feet for English and millimeters for the SI system. And what's commonly used is galvanized steel round longitudinal variable joints or galvanized steel spiral seams for round duct. And that's got an average loss of 0.0003. And for galvanized duct, it's 0.00027 to 0.0005, commonly used 5. Now, just a little clarification. This is based on 4 foot, and most rectangular systems today are 5 foot, but that's okay. You're not going to have that much difference. And I would use 0.0005. The right-hand side is the Darcy equation, as we said, and that's the sum of the loss coefficients times the section's velocity pressure. So if I have 3, 4 fittings, I can get the coefficients for each of those in the section, multiply that times the section velocity pressure, and that's going to be the total pressure loss of the fittings for that section. Where do they come from? This is an example. They come from experimenting data. And this is for a single flow fitting, but the ideas work for branch fittings or diverging flow fittings as well. You measure the static pressure at this plane 7, that's upstream of the test fitting. And again, at the plane 8, some diameters downstream. And you subtract off the friction loss as well as the change in velocity. Now, for a single flow fitting, the change in velocity is 0. But basically, that's the equation that's used to determine the total pressure loss of the fitting. And that's typically called the zero length dynamic loss because it's based on no friction. The friction is always calculated to the center line of the duct. And then if you get single flow values, you can actually do a regression of the total pressure loss to the velocity pressure, and that'll give you the loss coefficient. But if you're using branched fittings, then you're probably going to tabularize them based on the volume flow rates. All right, so I talked about the ASHRAE duct fitting database, and it's interesting, about 27 of the attendees do use the database. 63%, I think, was not aware. I don't remember the exact numbers. 9% did not use it. But it's a really nice program. You can actually purchase it in conjunction with the duct design guide. They'll give you a discount on it. If you do, make sure you get the spreadsheets. They're free, but it shows the examples in the duct design guide as well as a master spreadsheet if you want to use spreadsheets to calculate your losses. But it calculates the loss of round, rectangular, and flat oval duct and fittings, so all 3 shapes. Calculates and takes into account density, so you can change the air properties. You can kind of do it on the fly if you want, but it won't convert. Once you convert from IP to SI, you'll have to re-enter the values for the SI. The typical values that you need for density are humidity and elevation and temperature. It determines the pressure loss based on input dimensions and flow rates. You can look up a complete fitting loss coefficient table. You can print it or export it to Excel. You can look up fittings in table view by filter. So if you just want to look at round elbows, you can filter down to that and see what the round elbows are available. And you can create projects of duct fitting pressure losses. So you can continually enter for new fittings in one project, and it will save that project. And as I say, the results can either be an IP or SI. Here's an example for calculating the friction loss at 1,000 feet per minute. Length is 100. The roughness is 0.0003. And we input those datas, and it calculates the density based on prior inputs, and the results, the output. It gives you the velocity pressure, and most importantly, the pressure loss. You can say the same thing with the metric. Now, if I have an elbow, for example, this is a CD 3-1 die stamped elbow with R over D equal 1.5. I pull that fitting up. I put in this case, 10 inch, but I have an elevation of 5,000 feet. So I will have put that in prior, and that's going to give me a density of 0.062. So I need the 10, the volume flow rate, and I come up with the velocity pressure, the loss coefficient, and the pressure loss. So this particular case is a very low pressure loss. And there's the metric version of that too. Now, it's important to point out what friction is a function of. So if we did a comparison with 4 different velocities from 1,000 to 4,000 and 2 different roughness. So the standard galvanized for rectangular is 0.0005. Line duct rectangular is 0.003. So that's a factor of 6 difference. An example is using a 24 by 32 rectangular duct. So if we look at the difference in the roughness, even though it's a factor of 6, there's not very much difference in the friction loss. It only increased by 0.01 at the lowest velocity of 1,000. And even at 4,000, it increases a little bit less than 0.3. But if I look at how it increases from one velocity to 4 times that. So at 1,000, I'm on 0.05. At 4,000, I'm at 0.65. Same thing with metric. You can see the differences. But that's a factor of 13 increased in pressure loss when the velocity is increased by a factor of 4. So that's pretty significant increase just due to velocity. But it only increases by a factor of 1.2 to 1.4 when the roughness is increased by a factor of 6. So the roughness doesn't play near as much role as the velocity does. If you can keep your velocity down, you'll keep your friction loss right down. Now, we won't be able to use these in our design today, but these are the equations to calculate the equivalent round size for rectangular and flat oval duct. And you'll see in the flat oval, this inner equation to the brackets, that's actually the area of the flat oval. And this inner equation in the brackets is the perimeter. So when we calculate the flat oval, we're going to calculate the areas and then plug those into these equations. Now, the equivalent round is the size that has the same pressure drop at the same CFM. And the one thing I'll warn you is use the actual velocity for the actual dimensions. Okay. Here's an example of using it for rectangular. Plug in the numbers, and it's 19.9. In flat oval, here's the area of the flat oval. It's 294. The perimeter is 64. I plug those in and I get a 19-inch equivalent round size. Now, if the round size is known, then knowing one of the rectangular flat oval dimensions, you can solve for the other one iteratively, uh, or use the charts. I want to talk a little bit more about fitting efficiency. We'll do that with a series of elbows. And the first one is a smooth radius elbow with the R over D equal 1.5. That's got a loss coefficient of 0.11. For a smooth radius R over D equals 1, the loss coefficient jumps to 0.24. But look at the lower velocities to 2 decimal places, the loss is still only 0.01. Now, if I jump up to 4,000 feet per minute, it jumps to 0.24, so that's significant. But at 1,000 feet per minute, I can probably get away with using the R over D equal 1 elbow just as well. And then there's the 5-piece, R over D equals 1. That's got a fairly low loss coefficient. The 3-gore, 3-piece, is 0.34. Mitered with vanes, it jumps to 0.48. And the one we don't want you to use without vanes is a mitered elbow without vanes. That's got a loss coefficient of 1.19. But even at that, at the lower velocity pressures, the pressure drops only 0.07. Now, if you go up to 4,000, it's well over an inch. That's pretty significant. There's the metric version of the comparisons. Now, I want to talk about rectangular elbows. You can use splitter vanes, short radius with splitter vanes. I didn't put those out here, but those can become pretty expensive. And what you might find is without vanes, without the splitter vanes, the loss isn't that great. You might want to go that direction. But right now, I want to talk about mitered elbows, rectangular mitered elbows with turning vanes. And you can see that the best of all these is a single thickness vane with a radius of 2 and a spacing of 1.5. That's got a loss coefficient of 0.11, so fairly low losses. If I wanted to go with the double thickness and go way over here with R also equal to 2 and S equal to 2.25, that's still got pretty low loss coefficients, not as good as the single thickness, but pretty good. And if you want to use the double thickness, that would be the recommended spacing. R equals 2 and S equals 2.5. This is the metric version. All right, a couple things that we want to make sure the audience is aware of is vanes with trailing edges have been tested to have higher loss coefficients than standard construction. And a lot of the reason for that is they don't get installed perfectly and they cause more turbulence than they take away. Removing every other vane can more than double the pressure loss. Don't do that. It sounds like it's money saving, but it's really not. And the other important aspect is that turning vanes are typically 90 degrees. If they're used in elbows of other angles, the pressure loss will increase. Or if they're loose, as it's shown in this figure 514, you can see the 90-degree vanes aren't turning the air all the way to 90 degrees. So this is creating a lot of turbulence here. What we would recommend is make the outlet of the fitting the same as the inlet and then use a transition. But if you're in a different type of elbow, let's say a 45-degree elbow, you don't want to put 90-degree turning vanes in. Either leave it out or you have to make special vanes. Branch fittings also have associated, sorry about the voice. So the branch fittings also have associated loss coefficients. You can see a conical Y, 45-degree conical Y is the lowest, 0.15. 45 is still pretty low, 0.38. But a 45-degree entry is a little bit lower than the Y at 0.35. And then you have the conical of 0.44, and then a straight T, which is pretty bad, loss coefficient of 1.21. So it looks like this conical tap, this 45-degree conical, is the best. But what's missing? Well, if you got to turn the air 90 degrees, as you do with a 45-degree entry, you have to add an elbow. So you have additional pressure loss for the elbow plus additional cost of making it. So we recommend for 90-degree branches to use the 45-degree entry. All right, let's look at duct design overview. There's many steps to look at. Determine air volume requirements, locate duct runs, locate balancing dampers if necessary, determine the allowable noise level, select the design method, and select the initial size. Determine duct sizes based on the design methodology. Keep aspect ratios as close to 1 as possible, and determine system pressure requirements. Determine the design legs for both supply and return. Determine the required fan operating pressure. Analyze the duct to improve balancing, reduce material costs. Select the fan according to proper guidelines, and if you've attended the other sessions, you know how to do that. Analyze the design to make sure it meets the acoustical requirements. Select materials that minimize costs and meet SMACNA's duct construction standards. Analyze the life cycle cost of the design and commission the design to make sure it meets the owner's project requirements. So let's talk about the critical path again. The critical path is a section from the fan outlet to a terminal device with the highest total pressure drop for supply systems. Or there's one for return to the entrance to the fan inlet from the entrance to the fan inlet with the highest total pressure drop for return or exhaust volumes. So at least, let's talk about supply. One section, one path will have the highest total pressure. Other paths will have lower pressure requirements. Well, that difference is the excess pressure that the non-design leg has compared with the design leg. What happens if you don't make those equal? Well, air redistributes to the path of least resistance and you won't get the right airflows. So you have to balance the system. How do I balance? Let's say I have a design path of 1.5 and another one at 1. How do I balance that? Well, I could use a balancing damper to add that 0.5 inches, or I could use a smaller duct size with a higher friction rate, or I could use a less efficient fitting. Now, the last two also save money, so it helps you balance the system and lowers the duct system cost. So that's where we use a total pressure design in order to help us reduce the sizes. Selecting the design method, equal friction, just some pros and cons. You can read through them. It's easier to use. You can use a duculator, but it doesn't account for the friction or for the fitting losses when you're doing the design, at least not the way static regain does. You still have to calculate them. And the last thing is the optimum friction rate's not known. Is it 0.08? Is it 1? Is it 0.5? It's not known. And now in static regain, you might have larger duct sizes, but they're offset by smaller sizes in non-critical paths. And a non-critical path is the same thing as a non-design leg. Systems will be more balanced, often can use smaller sizes or less efficient and lower cost types of fittings in the non-design legs. But sizing is cumbersome. It may require iterations, which are best suited for a computerized duct design program. It can only be used on supply systems. We haven't developed the static regain method for return systems. And you must choose an initial velocity based on some guidelines. So let's look at equal friction design. Size all main and branch ducts at a constant friction rate per 100 feet, including the initial section. So whatever that is. That's one way. Calculate the total pressure loss for each section, supply and return. Use a spreadsheet if it's helpful. For each main and branch of a junction, be sure to account for the straight through and branch losses. Tabulate the total losses required for each path. Okay. Then determine which one's the critical, the one with the highest operating pressure, and determine the excess pressure for the non-critical paths. And then if you applied the total pressure design to that, you can look at balancing the non-design legs by using smaller sizes, higher friction rates. And then the last thing, you should perform an acoustical analysis in the system to make sure it's meeting your requirements. In static regain, you're going to determine the initial design. We're going to use the same method to compare apples to apples with a friction rate. And that's a chart that is specifies the acoustic design criteria. We'll look at that table. The static regain equation is shown in gray there. The change in static pressure is equal to the velocity pressure upstream minus the velocity pressure in the section minus the total pressure loss. We want that equal to 0. Use the junction upstream velocity to determine PV1. Size ductwork downstream of a VAV by equal friction method. Tabulate the total pressure loss required for each path from the fan to the terminal. Here's the development of the static regain equation. Basically, what I want to do is I want to make the static pressure here at 1 equal to static pressure at 2, or really it's the static pressure at 2 equal to 1. If you do that and go through the system, it'll be balanced, and then you end up with this equation. And if you solve this equation, then and it's equal to 0, then the static regain will have balanced the system. Now let's take a look at that. It's PV1, which is going to be a given for what I'm working on in the second section. PV2 minus delta PT, or the total pressure loss. So the lower the total pressure loss is, the more efficient fittings that I use, the higher PV2 can be, which means what? That means the sections can be smaller. So that's the whole idea behind static regain. Balanced system with smaller sizes. All right, so for static regain design, determine the critical path we're continuing on. Determine the excess pressure for each non-critical path. Design should be reasonably balanced, but the total pressure design method will allow even smaller sizes in non-critical paths. If there's still an excess pressure, consider using less efficient fittings. If the balance is 0.1 inch or less, you're in pretty good shape. Perform an acoustical analysis. So we're going to do a quick example. You can read this. Its temperature is 69. Elevation is roughly 5,000, so that you end up with a density of 0.061. Diffuser and distribution ductwork downstream of the VAV box has a pressure loss of 0.05, and the VAV block terminal units have loss coefficients according to the following table. And what that does, it allows us to add those loss coefficients into the respective sections. Now, as far as the first section, ASHRAE has a recommended duct airflow velocities to achieve the specific acoustical requirements. The first section is typically the maximum velocity. So you see in this case, duct location and shaft or drywall sealing, and I want a NC or RC 35. My maximum velocity should not exceed 3,500. And that's whether you're designing equal friction or static regain. You can see there's a column for a rectangular duct as well. Sizing the first section, let's do it with an example. The total airflow is 11,400 CFM. We want to size it for a maximum of 3,500. The ASHRAE database has a friction fitting that will actually do that for us, the CD11-3. And what we find is the initial velocity in the round section is 334 feet per minute. Now here's that section 11-3. I put in the CFM. I put in the target velocity, 3,500. absolute roughness. This time I use 0.00040. And it comes up with a diameter of 25 inches, a velocity of 3344, gives me the velocity pressure, and it gives me the friction loss per 100 feet for doing equal friction design. You can do the same thing with the metric version. And now let's go ahead and design the equal friction. It has a friction loss rate of 0.41. That rate's used to size other sections. I can use the duct fitting database CD11-4 to size that. And this says CD11-1 to calculate the pressure losses, but the CD11-4 already gives you the pressure losses, so you don't really have to use the CD11-1. But we also have to account for fitting losses, so a spreadsheet is used to calculate the data. Here's the CD 11-4. The target friction rate is 0.41, 7,400 CFM. And that gives me a size rounded off to 21 inches and a total pressure loss of 0.048. The actual friction loss is 0.437 inch per 100 feet. The metric version. Here's the spreadsheet. Now I'm going to look at section 2, which is off the transition of the fan. We already said it's 25. I've got a couple different types of fittings. This is an elbow. This is a branch fitting. I put down their loss coefficients because I can add those up to a total of 0.14. Multiply that times the velocity pressure in the section, and I get 0.08. And then the friction loss I've already calculated at 0.11. I add those together, and I get a loss for section 2 of 0.19. If I go on to section 2 with the 7,400 CFM, the duct size becomes 21 and velocity 3,077. I still have a loss coefficient of 0.14 for the T. Multiply that times the velocity pressure is 0.07. Add that to the friction loss, and it's 0.12. And I just continue to do that. This is the metric version of it. So the results are total pressure drops for each of the paths, the excess pressure, so it's the highest pressure drop minus the pressure drop required, and a deviation, which is an average percent away. So what's the design like here? Well, the highest pressure drops 1.3, so it's the path to box 9 and 10. Now, the static regain, I'm going to use this equation. And again, the first section is designed the same way with acoustics. But when I'm doing the calculations, and you can see here, this is section 2, has the same result as the equal friction because that's the first section. But I added a column. This is the regain column, which is the PV1 minus PV2 minus delta TP. When that's equal to 0, then I've got the correct size. There's the metric version for the first section. So this is where the iterations come in. The size upstream is 25, and I start out with that. My pressure drops too high. It's not shown here. But I got to go to the fourth iteration. So I went from 25 to 24 to 23 to 22-inch diameter. And a 22-inch diameter, the regain is 0.07. If I go one more, the regain becomes negative. I don't like negative, so I go back to the 07, and the size becomes 22 inches. Same thing with the metric. So looking at the static regain critical paths, now it's changed to section 4.5 and 13.14. So they both require a 1.16. Now, if you remember, the equal friction was 1.30. So this is already saving money in operating cost. So here's my critical paths going into sections 4, 5, and 13 and 14. This shows there's excess pressure in section 19. So we'll take a look at that. So this is comparing the static regain to the equal friction. You can see the equal friction has a higher pressure requirement, and it actually is a little bit better balanced, but it's pretty close. And that's due to the lower velocities in the symmetrical. But the general case is the static regain will give you a better balance. So that's the metric version of it. If I want to apply the total pressure method with the static regain, I'll go to that section 19. It's now 9. What if I lowered that to a size of 8, or 229 to 203 millimeters? What happens? Well, that makes this leg very close to the other two legs. We'll take a look at that. Static regain versus the total pressure. Now, the operating pressure didn't change, still 1.16, but the excess pressure went from an average of 5.1 down to an average of 3.8. And in particular, section 19 was reduced by an inch. So that in itself is saving money. And there's the metric version of it. So in conclusion, equal friction designs may not be well balanced. Now, it could be if you're using very low velocities and it's fairly symmetrical. It could be pretty well balanced straight out of the gate. Static regain design should be better balanced, and for the same first section should have a lower operating cost. First sections can be sized to meet acoustical objectives. Efficient fitting should be used in the initial design. We saw that with the static regain, that the more efficient the fittings, the higher the velocity pressure can be, which means smaller duct. Smaller duct sizes or less efficient fittings can be used after the initial design to help balance. And that's the total pressure method can be applied to equal friction. Usually not, but it certainly can be applied to static regain design. And with that, I'll turn it back over to Lisa. Lisa, are you there?
I am. If you want to stop sharing your screen, Pat, that would be great.
Did that work?
Yeah, perfect. Thank you. So I do want to mention to everyone, if you have a question that you would like to submit to Pat Brooks, please go ahead and type that into the Q&A panel. I also want to mention that, again, to receive PDH credit for today's program, you do have to complete the survey, which we will send to you about an hour after today's program. That'll come through an email thanking you for your attendance. And those PDH credits will be issued within 30 days of today's program. So I'm going to give everybody a moment longer to submit some questions. And in the meantime, I will remind you that our final session will take place next Tuesday. This is a rescheduled date from last week when it was supposed to be held on December 9th, I believe. So we rescheduled it to December 21st to same time, 10 to 11 a.m. Eastern. The topic will be stall detection and control in commercial and industrial fans. Dr. Jeff Sheard, president of AGS Consulting, will be our presenter. So hopefully you all can join us for that final session. So with that, let's get to Q&A. And I will stop sharing my screen so I can read the questions. Pat, the first question we have came in fairly early in your presentation. And this person is asking this question is on the pressure changes in pressure slide. Is the PS that you showed at the fan the static pressure rating of the fan? And you're on mute, Pat.
I could hear myself.
I'm going to go back in the slide presentation just so we can try and uh, pull that up for the gentleman who's asking. So it was on the pressure, changes in pressure slide, um, which
Down a couple more. 21.
could it be this one?
That's is slide 21.
It
Well, yeah,
sure
that's
is.
it. That's it.
So
Uh,
is the PS shown at the fan, the static pressure rating of the fan?
um, yeah, that's my understanding is the static pressure at the fan outlet is what that is. And if you have a static pressure inlet and that difference, that could be how the fan is rated. Uh, so yes, I'll say yes.
Okay. And then we have another question that came in, and this gentleman is asking, how does using static regain save on operating cost versus adding balancing dampers?
Okay, well that's two different things. You want the system to be balanced. So static regain is helps with the balancing, especially if you use the total pressure method. And uh, static regain inherently, and it depends just in comparison. You can design any system to any static pressure.
Mhm.
But if you use a comparison where you make the first section the same as you do equal friction, then typically the static pressure is going to require less pressure than the equal friction.
Okay. And I'm going to circle back, Pat, to the question that you had just answered about the PS shown at the fan, the static pressure rating of the fan. This is actually the slide that Tim, the gentleman asking the question, was referring to, which may or may not impact the answer you gave.
Yeah, officially the fan total pressure is equal to the fan static pressure minus the velocity pressure at the outlet. But my understanding from the fan manufacturers is they have a static rating that's on the chart is the difference between the outlet static pressure and the inlet static pressure. At least that's what I was told in one of your seminars. So the pressure, yes. So the pressure you're seeing there is not necessarily the uh, uh, the static pressure rating,
Mhm.
but it's the difference between the two is probably what you're going to see from a fan manufacturer's um, catalog.
Okay. And I know that at the beginning with the poll question we did, we asked about the duct systems design guide and if people were using it, not using it, or aware of its existence and purpose. So I think it's probably good to go back to mentioning the duct systems design guide. And could you remind people how they can get a copy of this?
Yeah, actually, the poll question was on the duct fitting database,
I'm sorry, you're correct.
but that's okay. You to get either one of them, you have to contact ASHRAE headquarters.
Okay.
I know they had a sale on the Duct Systems Design Guide when it first came out. It was around 120. I think they have a combo group that you can get the Duct System Design Guide and the duct fitting database uh, for a discount. But kind of pre-warn you, the duct fitting database, I think, is a licensed year, so you have to renew the license each year.
Hmm.
But I
Okay,
get it free, so I'm not sure.
that's good to know. Thank you. And one other question that I have here is, what is the most common roughness factor when determining friction loss?
Oh yeah, that's a good question. 0.0003 feet is what's used to create the friction loss charts. But depending on what you're doing, if it's rectangular, it should be 0.0005. And if you're doing spiral with 10-foot length, it should be 0.0004. Now, and as you saw, the roughness doesn't make a huge difference. So I would use probably an average of 0.0004.
Okay. Very good. Thank you for that information. And I do know that we are at the top of the hour. And let's see, we have one more question that's come in that I think we can get to for those who are hanging around. And this question, Pat, is if we calculate P total loss based on the methods described in your presentation, is there anything special we need to do to determine the P static to specify the associated fan? And would asking for a fan with P static equal to the P total be sufficient?
Yeah, as far as I understand from fan manufacturers, if you tell them what the static pressure requirement is at the outlet, and that difference is the total pressure minus the velocity pressure at the outlet, and you do tell them the same thing at the inlet, they should be able to give you what the fan requirements are.
Awesome. Very good. Thank you for that feedback. And I do want to remind people that the recording of today's presentation, as well as the PDF version of Pat's slides, will be on the Odell website within about 48 hours. So please feel free to go there and use these as references. Pat, I want to thank you for your time and expertise today. It's been really informative. And I also want to thank the audience for their participation as well.
All right. Thank you, Lisa.
Thank you, and thank you, everyone. And we look forward to seeing you for the next session on the 21st. Everybody, take care.